It's time to talk about crystalline solids. And crystalline solids are, well, as you might guess, crystals. And what makes something crystalline is when you have the atoms arranged in very regular patterns that repeat over and over again. And so there is a lot of high degree of order associated with that crystal. So if this is your crystal, that would mean then that you could predict what where the other molecules are that grow out from here because they will follow a very predictable pattern. Now, because of this high degree of order and the fact that you have repeating structures that reinforce their location over and over and over again, it allows for a technique known as X-ray diffraction or X-ray crystallography. So the way it works, and this is a very simplistic sort of model, but the way it works is you take your crystal and you put it in the beam of an X-ray. And that X-ray then beam is shot at the crystal, and every one of the electrons, they have electrons. Every one of the atoms has electron density surrounding it. And when the X-ray hits those electron densities, they get diffracted. And you can collect the diffraction pattern on the other side of the crystal. And doing a whole heck of a lot of math, you can take a look at each one of these diffraction dots and back calculate to the locations of the atoms that generated them. And because of that, it allows you then to solve three-dimensional structures. What's interesting about this whole thing is that you might be thinking, well, you could probably picture things that you know are crystalline. You can say, well, I know that salt, sodium chloride, forms crystals. So it's a crystalline solid, which is true. So if we were to make a list of the things that commonly show up as crystalline solids, a salt would be one of them. So I have to spell crystalline. I hope I spell it right. If I don't, you know what I meant. Crystalline solids are salt, sugar. You know that can be. So this is ionic here. Salt is ionic. Sugar isn't ionic. It's called a molecular solid. So this is ionic. This is a molecular solid because it's just repeating molecules. That's a molecular solid. And then you can have a metallic solid. So some metals can also form crystals. So there are metallic solids that can also form crystals. So we'll look at some of these things. But what's one thing that, and I just want to point this out, is in my business, I'm a biochemist, and we can actually crystallize proteins and DNA and then do X-ray crystallography on those and get pictures, the three-dimensional structures that then we can use to study those giant molecules. And in my field, we do drug design and drug trying to identify things that could be acting as drugs. And crystallography is a really important tool when you're trying to figure out how certain drugs bind to proteins, protein targets. So it's really cool, very powerful. If you're interested in that kind of stuff, that's something you'll cover in biochemistry if you wind up taking it. I thought I would just show you what a protein crystal looks like. These are some different types of protein crystals that have been made. These were actually, I found this on Wikipedia, they were made on the space shuttle, which I thought was interesting. But they're just very beautiful, and I would never picture something like a protein, which I usually associate with like egg white or muscle tissue, that kind of stuff. Well, these individual protein molecules can be crystallized and they look just like a precious gem, you know? And so that's pretty neat. So I thought I would just point that out to you. So let's talk a little bit more about the crystal itself. So first of all, how do you make a crystal? Well, you need to get a pretty concentrated solution of whatever it is that you want to crystallize. And then a lot of times it depends on what you're looking at. But usually you start from a warmer condition and then you allow the sample to cool slowly. And that gives the particles a chance to arrange in very regular and patterned in regular patterns, and when they're really positioned well, they maximize those attractive forces, and it puts the the collection in the minimized in a geometry where the energy in the system is minimized, so it's the most stable. That's what this means. Uh, that's just means stable. Okay? And you will, like, for those of you who go on to organic chemistry, for instance, you're going to do this. You're going to actually make crystals. It's a really common technique used for a lot of purposes, and you will do that. So you'll get your chance. But in this part of this course, we're going to look at how do we study and think about the crystalline solid. So when the crystals are formed, the way that the particles arrange themselves is known as a crystal lattice. And so that's just a way to describe the scaffolding that allows for the crystals for the molecules or the atoms in the crystals to be arranged. And within that scaffolding, that crystal lattice, what you will find is that there will be a smallest unit that repeats over and over and over again. So it's the smallest repeating unit. And I think it would be good to include the idea that it repeats here. So the smallest repeating unit. Smallest repeating unit. Okay? And that shows the pattern of the arrangement. That smallest repeating unit is what we call the unit cell. So that's called the unit cell. So let's talk a little bit more about the unit cell and what we can learn about that solid by examining the unit cell. So unit cells are three-dimensional, so you got an X, Y, and Z plane, so they are in 3 dimensions, and they can contain multiple layers of particles. It just depends. It's just whatever the smallest unit is that repeats, and these things just repeat over and over and over again to build that structure. So you could, so it will do this. Over and over and over again in all 3 directions, X, Y, and Z. And each particle is called a lattice point. So if each particle is called a lattice point. So if we look at this atom right here, that's part of an atom, but that whole atom, if you build it all the way out, see, they're just drawing them as spheres here. That's your lattice points. And then you have lattice planes, and these are the planes that connect equivalent points. So you'd say, here's one plane, like that. Here's a plane. And they just keep building in that way, and they can build up and build down and build out. So that's the general idea of a unit cell. So there are 7 common unit cells, and you can see they have different shapes. And honestly, there's when you start talking about protein arrangements, like I mentioned, protein crystals, there can even be more. The one we're going to focus on, and honestly, you guys, I want you to be aware that there's other shapes that repeat, but the truth is, the one we're going to put our focus on in this course is the cubic unit cell. And it's exactly like you think. It's a cube where you have each edge of the unit cell is equal in length, and all of the angles are at 90 degrees. And that is what we're calling the old cubic unit cell. And so we're going to dig a little deeper into the cubic unit cell, and that's what I want us to focus on. You can do similar types of treatments, albeit they will be more complex because they're not following this nice all sides are equal 90 degree, because you'll see there's some geometry that has to actually be done to figure out how long these lengths are. And the geometry just gets a little funkier as we move into these other areas. So I'm going to just say, let's focus on this one for this class. This will keep you busy anyway. And actually, I have trouble. I'm one of these folks who have trouble with envisioning things in 3 dimensions. And so I really struggle when I start getting more complex than a cubic cell. I don't know if it's what causes that in my mind, but I really do. And so it turns out, though, what we can learn from this is going to be very good to apply in other cases if you happen to be. So when would you worry about stuff like this? Well, I could envision that if you were in geology or materials science, you'll have to, and even some areas of chemistry and biophysics, those kinds of things where you might be doing structural determinations, then you'll probably have to be better at picturing these than I am. At any rate, let's move on. Speaking of cubic unit cells, there are 3 that we're going to look at in this class. These are the 3 that we'll find. We have something called the simple cubic cell, the body-centered cubic cell, and the face-centered cubic cell. And we'll find out, and I'll go into each one in detail, but we'll find out that when we look at how many total atoms you will find within the cubic cell, you'll find 1 whole atom in the simple cubic. There's a total of 2 whole atoms in what we call the body-centered cubic. And then in the face-centered cubic, we will see that there are 4 atoms total. Then, based on the value of R, where R is the atomic radius, so the radius of the atom, we can calculate the edge length, and the edge length is, well, I gotta stop drinking coffee. Okay, the edge length is the distance from of the center of one atom to the center of another atom. So if I draw it in, you can kind of see. So each edge length then goes from the center of one atom to the center of the other. So there, okay. So I have a shaky hand this morning. Anyway, so you got that going. And so that's kind of how we think about that. So it's really easy to see then if you were to compare in these simple cubic, since the atoms are touching, there's one, I'm going to switch my pen color here to illustrate something. So there's one radius and another radius of the next atom, the two together will come up with this edge length. Now, it gets a lot more complicated with body-centered and face-centered because no longer are the atoms in the corners touching. So now you'll have to like go diagonally across, because in the body-centered you'll find that there's an atom found in the very middle. And so you have to go across the several radii. And so that's when you, and the same kind of thing is happening with face-centered. So then you have to start using like Pythagorean theorem. Remember, a squared plus b squared equals c squared. And that's where the geometry part comes in. But these are the formula you can use to calculate the edge length of a unit cell. And we'll show you how that works later. And then packing efficiency. Turns out that the most densely packed unit cell is the face-centered cubic. It has a 74% packing efficiency. In other words, in terms of the volume of the unit cell, 74% of that volume is just taken up by the atoms. 68% of the volume of the unit cell for body-centered is taken up by the atoms, and only about half, 52%, of the space found in the simple cubic cell is taken up by atoms. So let's dig a little deeper into each of these types of unit cells. So when looking at the cubic unit cell, we will find that there are 8 particles, could be atoms. For now, we'll just think about it in terms of atoms. There are 8 particles or atoms in the tube. So, and we say particles because when we get to more complicated structures like protein structures, it may be actually, a particle may be a group of atoms. Sounds weird. For this class, we're going to just let one particle equal one atom. And what you'll find is that there's going to be one atom at each of the corners of the cube. And I'll show you this in a diagram in the next slide, but 1/8 of that particle then lies within the cubic cell. So since there are 8 corners and 1/8 of an atom found in each at each corner within the cubic cell, you can say that there's a total of 1 atom or particle in each unit cell. And I've already mentioned the edge length of the unit cell is twice the radius. So let's examine this a little better so you can, especially this part, so you can kind of see how is it that there's 1 atom in a unit cell. And that's where it helps to have a diagram to show that. So hopefully this will help you see how we can come up with a simple cubic unit cell having just 1 atom encased within it. So what you're seeing here is, here's the cubic cell, and as I mentioned before, the edge length of the simple cubic cell is really just 2 times the radius of the atom that's involved. And so that's something to keep in mind. But here's the thing. Each one of these corners, okay, each one of these corners is shared by 8 other cubes. It's connected to, not shared necessarily, 8 other cubes. Each corner is connected to 8 other cubes if you count the different directions that they grow out. You got some coming this way, you got things growing up, all the different cubes you can see in all the different directions. See if you can find that, but that's what's happening. So this 1 atom that you see here or here, every one of the atoms that are in the cubes are shared by 8 other cubes. And so what that means then, if we were to think about what portion of the atom exists within the actual unit cell cube, well, just 1/8 of that atom belongs inside of that cube. This is what is being shown in this sort of reduced view. So if you just took this whole thing here and cut away just the cube itself, you would see that there's 8 atoms. I mean, 1/8 of an atom at each of the corners. And since there's 8 corners in a cube, that means that if you have 1/8 of an atom per 1/8 of an atom per corner, and there's 8 corners, you multiply them, you get 1 total atom per unit cell. Now that obviously it's pieces of atoms and they all add up to 1 total atom. So it's not a single atom, it's not just one single atom. It's 8 pieces of an atom that add up to the 1 atom that's found here. We'll find out in a little bit why that's important, because we're going to use that information to calculate density of the crystal, of the unit cell. And that, I like doing that because actually in my mind it does something that is very interesting, and I'll point that out when we get there. All right, so let's go to the next part of this. Somehow I accidentally, and I apologize for this, I can't undo this, so I'm just stuck with it. I did some white thing. Anyway, doesn't matter. You can see what it's supposed to be. So getting at cubic unit cells, continuing on now, our next one we're going to deal with is called the body-centered cubic cell. So the simple cubic cell had 8 particles associated with it, 1 at each corner. Well, we're going to build on from that. We still have the 8 particles at the corner, at each corner, or 1 particle at each of the 8 corners. But now, for body-centered, and it's called body-centered because in addition to that, there is another atom found in the very center of that unit cell. In this case, we have 1/8 atom, just like before, at each of the corners, and we have 1 in the center. So if we add that together, we have 2 atoms total. And because we have 1 from the corners and 1 in the center. And I've already mentioned about the unit cell length, so I'll move on from there. But now that I see this, I realize that I have to make one little change. It's 4R. So it's missing the radius. How stupid. Anyway, so that's what you get from that. That's what the unit edge length is. Again, I think I just want you to kind of see a picture that shows what's going on here. So just like we did before, we got the cubic unit cell, the simple cubic, had 8 atoms in each of the corners. Now there's just an added complexity. What we do, and we have those same 8, similar kind of situation, 1 atom per corner, 1/8 of an atom per corner, just like in the simple cubic. And now inside of the entire cell is an entire atom. So if we look at, again, the sort of cutaway view, we can see 8 corners, each with 1/8 of an atom. That gives us 1 atom, we've learned that, and then there's 1 in the center. So if we wanted to calculate then the atoms per unit cell, we would combine the 2 things. The 1/8 atom at each of the 8 corners, that gives us 1 if we multiply it out, plus the 1 in the middle, so we have 2 atoms per cubic cell. So the body-centered cubic cell occupies more of the available space with atoms than the simple cubic. That's where we talked about the 52% and that whole thing in that one original table. And this is why. There's two whole atoms, essentially, 2 atoms worth in this unit. Now the face-centered cubic cell has the most particles associated with it at 14. It has the 8 that we know, that one at each corner of the cube, so that part is kind of, a theme for cubic unit cells in general. But then at each of the faces, and there's 6 faces, there's an atom associated with each of those. So that's a total of 14, 8 plus 6. So if we were to look at things, then we have the 8 corners with 1/8 atom. That's true of all of the cubic unit cells. But in this case, in addition to that, we have 6 faces of a cube, and each face has 1/2 of an atom. It's shared by 2 atoms. It's shared by 2. Each face is shared by 2 cubes. And then we've talked about the edge length before, and again, there's a little typo here that I just caught, and so we're going to fix that. It's 2 times the square root of 2 times r. Now, so that you can keep that in, r again is that atomic radius. So this is forgetting the r. So it goes down like that. And here's a picture of what's going on there. So we have each of our corners, and then in addition to each of the corners, then we have the faces. And each face is shared by 2 unit cells. So that means, so it's easier to show that one. This one grows up here. So you got your cube here. So you got 1/2 of the atom is in that cube, and the other 1/2 of the atom is in that cube. So we can again do the cutaway, which I think is a useful thing to do, so you can see that there's parts of atoms in there, and if you add all parts together, you get the 1/8 times 8 corners, and you get 1/2 times 6 faces. And when you add it together, there are 4 atoms in that one cubic, in a face-centered cubic cell. 4 atoms. So now we're going to put this stuff into action. And this is the thing I referred to before. We're going to calculate the density of solid crystalline aluminum. We're going to calculate it in grams per cubic centimeter, which is how we usually write out densities in grams per cubic centimeter. For solids and for liquids, we tend to do that. So in here, we're going to look at a case where we have a metallic solid, aluminum, that has a crystalline structure. And it has a face-centered cubic cell. So when it crystallizes in a face-centered cubic cell. And we're given the radius of the aluminum atom, and that's at 143 picometers. And a picometer is 1 times 10 to the minus 12th meters. So it's pretty small. So 1 times 10 to the minus 12th, that's what pico means, meters, okay? So that's it. So if we were to write this out, we could write this as 143 times 10 to the minus 12th picometers. Sorry, meters. So that would be meters. That's what it would be. So 143 picometers would be 143 times 10 to the minus 12 meters. Or you could write it as 1.43 times 10 to the minus 10th meters. So it's equivalent to either of those. Those are the same thing. All right. So let's prepare to solve this problem. The atomic mass of aluminum, which we need to know, is 26.98 grams per mole. So I just looked that up, and from the periodic table. Okay, so 26.98, the molecular weight or atomic mass of aluminum. Okay, we need that. All right, so let's think about this. So we need to figure out grams of aluminum in 1 unit cell. And the way we go about that is we use the information that we already know. We know that we have a face-centered cubic cell. And if you remember, for a face-centered cubic cell, there are 4 atoms. Okay? So there's 4 atoms. So we have to figure out how many grams 4 atoms of aluminum are. So we have to, that's where we start using things like Avogadro's number. Do you remember Avogadro's number? So we want to convert 4 atoms to grams of aluminum. So to do that, we simply use, I think you can use, and there's exactly 4 atoms. So this has an infinite number of significant digits because there's exactly 4 atoms in the face-centered cubic. Okay, so there's 4 atoms of aluminum. All right, per face-centered cubic cell. And what we want to know is how many grams of aluminum are there per face-centered cubic cell. So I know there's 4 atoms. So now here's where I know that I want to go to moles and then use the molecular weight to get to grams. That's my idea. So I can go to moles of atoms simply by dividing by 6.022 times 10 to the 23rd atoms of aluminum. That gives me moles of aluminum. And then I just multiply that by 26.98 grams of aluminum per moles of aluminum. And that cancels out, atoms cancel out, and what I'm left with are grams of aluminum per face-centered cubic cell. So let's multiply that out. And so when I do that, I get 1.79. Since I have 4 significant digits, I'll go with that. 1.792 times 10 to the minus 22nd grams per face-centered cubic cell. So that's grams of aluminum. So that tells me how many grams. Now I need to calculate the volume of that cubic cell. So I need to figure out what the volume is. And here's where I need to be able to calculate the edge length of that cubic cell. And that's where I can remember that the edge length is 2 times the square root of 2 times the radius. Okay? 2 times the square root of 2 times the radius. This is our edge length. Okay? And that's important because then if I'm looking at my unit cell, my edge length is this length right here. And then if I know that, all I need to do to get the volume of that cube is cube the edge length. Okay? So let's first calculate our edge length. Okay? 2 times the square root of 2 times 143 picometers. All right? And if I then go through with the math, that's going to be equal to, I get 404, okay, 404 picometers. Okay, and since I only have 3 significant digits with my radius, I'm going to keep it at 3 sig figs here. Now, what I do at this point is, since I know I want to get cubic centimeters, I convert this first to centimeters. So I need to get 404 picometers to centimeters. I do that before I do the cubing because there's less room for error when you do it that way. So I convert picometers to centimeters. That's the next thing I do. And there are many ways you can do this, and if you're comfortable with other ways, that's fine. But this is how I do it because when converting a cubic picometer to a cubic centimeter, it's a little more complex, and that's where I see a lot of students make quite a few errors. So instead of doing it that way, what I do here is I first convert my picometers to centimeters, and then I cube it, and then I'll have my cubic centimeters. So I want this in centimeters, cubic. So I know I can just keep going here. So that's my edge length. And I know that there is, I just mentioned this, exactly 1 times 10 to the 12th picometers, not minus 12. There's 1 times 10 to the minus 12 meters per picometer, but I have 1 times 10 to the 12 picometers per meter. It's just how you have to pay attention to what that means. So I know that there's a 1 times 10 to the 12 picometers in every meter. And every meter is 1 times 10 to the minus 12 picometers. Students get that messed up a lot too when they're doing these conversions. So this cancels out, that's good. And then I just know that 1 meter is equal to 100 centimeters. Okay? And so I cross that out. Now I got things converted to centimeters, so if I add all this up, I should get what I need for the edge length of my unit cell. So that comes to 4.04 times 10 to the minus 8th. Now, I did my rounding right away. I think if you chose to, you could have put 4.04 times 404.49. It could have been that. I chose not to keep that. You could, but then you'd have to remember that your significant digits are still 3. So I just did my rounding at that point. If you did it that way, you may get a slightly different answer, and but in the end, things will be pretty close. All right, so now I'm going to shrink this down a little bit and continue on. So what I want now, this is in centimeters, and I want to calculate my volume. Is going to be 4.04 times 10 to the minus 8th centimeters cubed, because that's how you calculate the volume of a cube. And so if I do that, I get a very small number, as you might guess, because we're talking about a really small unit cell. So this would be 6.59 times 10 to the minus 23rd cubic centimeters. And so now I know my grams, and that's per face-centered cubic. So now I know my grams of aluminum per face-centered cubic, and I know my volume for this cubic cell. So all I do is divide my grams by my volume, and that should give me the density of this unit cell. So to do that, then I got 1.792 times 10 to the minus 22nd grams of aluminum divided by 6.59 times 10 to the minus 23 cubic centimeters. And so the density is, and I'll punch that into my calculator, I get 2.71 or 72 grams per cubic centimeter. And so this is the density of my face-centered cubic cell with aluminum, But let's compare that to the actual listed density for aluminum, which I will look up and write down here and see how they compare. So I just asked Siri, I have on my iPad here, what is the density of aluminum? And Siri gave me this answer, 2.7 grams per cubic centimeter. So guess what? And this is the part that I find neat. I kind of told you there's some part I found neat here, is that the density, the known density for aluminum or whatever thing we do this for, is going to be consistent whether you're talking about 20 kilograms of that substance or the density of its unit cell at the smallest repeatable unit. The density is preserved all the way from the big bulk down to a single unit cell. The density of that metal or substance of the crystalline solid is going to be preserved all the way down to its unit cell. So if you can calculate the density of the unit cell, you know the actual density of aluminum, even if it was a big chunk. I find that really interesting that it's preserved in that sort of level. So you're going to do calculations like this, and you're going to play around with different aspects of these calculations. Um, and what's interesting to me is that things like density are consistent even down to the molecular level, which is pretty cool for me. I'm a chemist. I should love stuff like that. So I really like doing those kinds of calculations, but there's a little bit more to this chapter too, and I'm to what I'm going to cover in this area. First of all, I want you to know that there are different types of crystalline solids, and so we're gonna classify these, okay? And and they are oftentimes we're dealing in terms of what makes up the solid. Is it ions? Is it covalent? Things like that. Molecular solid. So we'll look at those. So here are the choices we have, or the classifications. We have molecular solids. So we have the repeating units are atoms in those cases. The repeating units are molecules. Example, sugar. Sugar is a molecular solid. Okay. And then in addition to that, we have ionic solids. So we have ionic solids. We have atomic solids. So that's when you have particles are atoms. In those cases, the atoms are held together by dispersion forces. You know, they're not dipoles or anything. We also have metal atomic solids, and we have network covalent atomic solids. So atomic solids are made up of one type of atom. So in the case of we have, you know, these examples here. Metallic, well, we just dealt with one, aluminum. Network, diamonds would be a network covalent solid. Okay, and so that's kind of what we're the different types of solids. So here are some examples of those. We have the molecular solids. These are composed of molecules. Okay, so all the different lattice sites are molecules rather than just single atoms. So we got carbon dioxide, water, so ice. That's sucrose or sugar, and you know the molecules are held together by different forces of attraction that we know. If they could hydrogen bond, dipole, dispersion forces, depends on what it is that's binding, whether or not they're molar. Sorry, molar. Polar. If they're polar or nonpolar, then that will define which of these winds up working out, being holding them together. They tend to have low melting points, and low melting points considered anything below 300 degrees Celsius because they're held together by these generally weak attractive forces. They're not held together by ionic bonds or something like that. Okay, now moving on here. And then you have your ionic solids, and that's where the lattice sites are occupied by ions, okay? And they're held together by those Coulombic forces, the opposite charges that are attracted, and so the cations attract the anions all around it and vice versa. So that's kind of the arrangement you would find. One of the features of ionic solids is they have very high melting points and boiling points. Very high, extremely high. Okay. And that's because the forces that hold them together, those ionic interactions, are very strong. It takes a lot to break them apart. Metal solids are really interesting. So they're the metals essentially it's almost like a communal kind of thing. So this is some of the properties of metal solids are, you got a bunch of cations that actually fill up the lattice points, and the there's so you think, oh, there's a bunch of cations around, and those things are going to repel each other, but it turns out that what makes them communal is that there is a whole bunch of electrons that are being shared together by all those cations. So one of the reasons, for instance, you think about this, you got a bunch of cations around with the electrons just kind of flowing through. Well, that's what makes these cations, these metal solids being able to conduct electricity, because electricity is the movement of electrons. So since the electrons are just kind of loosely held by all the different nuclei, you get these kind of, like I say, they remind me of a communal. I don't know if that's a communal group of electrons being shared by all, kind of communistic or socialistic kind of solid that way. And this is kind of demonstrating that. So they have these mobile electrons that are being shared throughout. This is kind of the idea here that I just mentioned. I just find that it's the valence electrons that are flowing, and so it's just really interesting to me. And honestly, I try to wrap my head around this, and I still get confused. But it makes sense because these things are really good at conducting electricity. So you would think, well, they must have the ability to let go of their electrons and allow movement of electrons, and that's exactly what happens. So it's a little goofy to me, but that's what it is. It's something that I have to accept because I can accept the description and I can see the different properties of metals and how this would help explain that. But at the same time, when I'm trying to picture it, I do struggle with it too. But it's interesting to me. And then there's network covalent solids. That's where you have pretty high pretty high melting points, which makes sense because you have these networks of covalent bonds hooked together. So, so things like graphite, diamonds, those things tend to be network covalent solids because they're just an arrangement of carbon in both cases that go on forever and ever, but they're very regularly arranged, so they are crystalline, and that's why you can get the two different types. It's funny, both are polycarbon. You have graphite and diamond, and yet graphite soft, diamond's really hard. That kind of thing happens, and so the crystalline arrangements can change the properties as well. So that's what we have for crystalline solids.